High in the mountains, thousands of glacial lakes sit in frozen isolation. On the surface, the water is utterly calm, locked away beneath towering peaks. A massive shelf of glacier shears off and plunges into the basin. The impact generates a displacement wave that ripples outward with immense kinetic energy. That wave slams into the natural barrier holding the lake in place. The wall fractures. In seconds, millions of cubic meters of water, ice, and rock tear down the valley at highway speeds. Downstream, the destruction is absolute. Steel bridges vanish, hydropower stations are shredded, entire villages are wiped from the map in a matter of minutes. These alpine basins are heavily pressurized, volatile hazards, hovering directly above populated valleys, waiting for a single trigger to release. This phenomenon is called a Glacial Lake Outburst Flood, or GLOF. As temperatures rise, glaciers melt and pool in depressions left behind by the retreating ice, creating reservoirs held back by natural walls. The mechanics of failure are a matter of hydrostatic pressure. Imagine filling a balloon with water. As the volume increases, the outward force stretches the material to its limit. If a tiny tear forms, the entire structure instantly gives way. While thousands of these lakes exist across the Himalayas, the Andes, and the Alps, only a small fraction possess the exact structural vulnerabilities required to trigger an outburst. For those that do, warning times are almost zero. Once the barrier breaches, the ensuing flood accelerates so rapidly there is virtually no time for downstream communities to react. The threat of these lakes is rooted in the hidden fragility of the natural container holding the water back. The setup for these disasters takes decades. Warming global temperatures accelerate glacier retreat, scraping deep gouges into the earth that steadily fill with seasonal meltwater. The barriers holding this water in place are called moraines. They are simply piles of loose rock, sediment, and leftover ice bulldozed forward by the moving glacier centuries ago. An engineered dam relies on solid concrete. A moraine is porous gravel. Water seeps through, eroding the structure. The Himalayas were formed by a continental collision, creating steep ravines. When a moraine bursts, gravity turns the valley into a high-speed funnel. Geologic history and modern warming have combined to construct these unengineered, highly unstable reservoirs at the highest and steepest points on the planet. The final breach requires a catalyst, a sudden avalanche of snow, a massive rockfall, or a deep tectonic earthquake can provide the jolt needed to shatter a moraine. These events often merge into cascading hazards. During the 2013 Kedarnath disaster, extreme monsoon rainfall compounded with intense glacial runoff, causing downstream destruction that scattered immense boulders directly through populated centers. As the flood travels, it scours the valley floor, rapidly transforming into a dense debris flow. The water sweeps up multi-ton boulders, towering trees, and thick mud, exponentially multiplying its mass. By absorbing the solid mass of the mountain itself, the floodwater becomes a blunt force battering ram, guaranteeing the total erasure of anything in its path. Today, hundreds of these expanding lakes sit above high-risk glaciated regions in the Indian Himalayas, directly threatening critical hydropower infrastructure and large communities in states like Sikkim and Uttarakhand. Because these peaks are entirely too remote to maintain a continuous human presence, scientists rely on overhead observation. Massive satellite networks track shifts in lake expansion and snow cover. High-resolution LiDAR scanning and automated water-level sensors map the terrain in 3 dimensions, allowing researchers to detect minute shifts in ice density and hydrostatic pressure before a natural dam reaches its breaking point. Maintaining ground-based instruments in this environment is incredibly difficult. Sub-zero weather, shifting ice, and sheer altitude constantly destroy equipment. In an environment hostile to human survival, continuous observation from space remains the most reliable line of defense. Once a high-risk lake is identified, engineers can attempt to diffuse the threat physically by safely siphoning off the water to lower levels or excavating reinforced spillways through the moraine. They relieve the pressure. Disaster management relies increasingly on predictive digital twins. These AI-driven models map entire mountain ranges and simulate fluid dynamics to plot exact flood paths down to the meter, long before a drop of water spills. But on the ground, human survival comes down to strict preparation. It requires mapping clear evacuation routes beforehand and abandoning low-lying areas the second the first warning siren sounds. Climate change ensures these high-altitude reservoirs will only continue to grow. Yet, through predictive AI, robust civil engineering, and relentless remote monitoring, we have the tools to track nature's quietest threats before they strike.